Bismillahirrahmanirrahim. In this video, we are going to discuss selected harmonic elimination PWM technique for the inverter circuit. So in this PWM technique, we construct output voltage waveform by controlling the angle of the edges in such a way that our selected harmonics are cancelled out. And because of this, it is said to be a selected harmonic elimination technique. Okay, so for selected harmonic elimination, there must be the half wave symmetry and the quarter wave symmetry in the inverter output voltage waveform. So if these two symmetries are going to exist, then according to Fourier series expression, we can cancel out an. The en will be equal to 0. So we have three Fourier series coefficients. A naught, that is the DC component, that will become 0 if we have the half wave and quarter wave symmetry. En, that will also become equal to 0, and only Bn will exist for odd harmonics. So while constructing the inverter output voltage waveform, we ensure that there exists half wave and the quarter wave symmetry in the inverter output voltage waveform. Okay, and for quarter wave symmetry, we can evaluate the Fourier series coefficient Bn with the help of this expression, that is 8 by time period integration from 0 to t by 4, that is the quarter cycle, integration of the signal and its product with sine of n omega t with respect to d omega t when our limits are in the form of angle. Okay, now let's draw the inverter output voltage waveform, which have the quarter wave as well as the half wave symmetry. So let's suppose that this is pi by 2, the quarter cycle, this is second quarter cycle, this is 3 pi by 2, and this one is 2 pi. And I have a set of pulses which is centered at, let's suppose, pi by 2. Over here. The center point of this pulse is this one, and its negative part is over here, which is centered at 3 pi by 2, right? So in this pulse, you can say there exists the half wave symmetry as well as the quarter wave symmetry, because if you look at around pi by 2, the equivalent part is available in the next quarter cycle if we flip across that one, and if you flip and invert across this half cycle point, you are going to get the same waveform. So quarter wave and the half wave symmetry exist. Now if I add another pulse in this one, let's suppose over here, then I will have to add this part over here as well to maintain these two symmetries, and to maintain this symmetry I will have to add these parts in the negative part as well. Okay, now let's mark the angles. Let's suppose that this angle is alpha 1 and this angle is alpha 2 from this reference point. So then this angle will also be alpha 1 and the angle of this notch will be alpha 2 from the center point. And then this angle alpha 1 and this angle alpha 1, both of them will be same for this second set of notch, for this notch as well as for this notch. And if we look at the angle for the center point, let's suppose this is alpha 2, so then this will also be alpha 2, and these angles are exactly same what we have in the first quarter cycle. So if we know alpha 1 and alpha 2, if these two angles are known, we can adjust the spectrum accordingly to cancel out certain set of harmonics, because these angle will change the Bn. An will be 0 because we have the half wave symmetry and the quarter wave symmetry. So An will be 0, A naught will be 0 as positive and negative areas are equal. So only Bn will be there, and the Bn will change by the change of these two angles alpha 1 and alpha 2. Let's suppose that this is plus Vs and this is minus Vs, that is our output voltage is varying between these two limits. So now if I calculate Bn for this waveform, So for Bn I can write down the expression 4 by pi integration of our signal multiplied with sine of n omega t. So first of all I am going to consider this part. So let me call it part 1. So it is from 0 to alpha 1. So integration from 0 to alpha 1 of Vs into sine of n omega t with respect to omega t. And then taking the second part of our signal, I am going to consider the quarter cycle because we are taking Bn is equal to 8 by t. So this is the second part of the quarter cycle. So for that the limit will be starting from this point till this point, and this is the angle alpha 2, and over here the angle is pi by 2. So integration from from alpha 1 to pi by 2 of Vs into sine of n omega t with respect to d omega t will give us the area under this second selected part. So we are going to consider only the quarter cycle. Rest of the quarter cycles will be having the same area. Okay, so Bn now can be simplified, and we can write it like that for Vs by n pi, and we have minus cos of n omega t, and its integration limits are from 0 to alpha 1. Then is the second part minus cos of n omega t, and the integration limits are from alpha 2 to alpha 2 to pi by 2, right? So now if I apply these limits and write down this expression, this will be equal to 4Vs by n pi into minus cos of n alpha 1 plus cos of 0 n or cos of 0 minus cos of n pi by 2 plus cos of n alpha 2. And over here the n will be an odd number, because when there exists the quarter wave symmetry and the half wave symmetry, only odd harmonics exist. So Bn can finally be written as 4Vs by n pi into 1 minus cos of 0 will be 1, right? 1 minus cos of n alpha 1 plus cos of n alpha 2 for the odd harmonics. Cos of n pi by 2 will be equal to 0 for any value of the n in the odd numbers. Okay, now to cancel out the harmonics, this Bn should be equal to 0. If I say that if n is equal to 3, I want to cancel out the third harmonic, then for n is equal to 3, this Bn should be equal to 0. So for that, this part cannot be 0 because Vs will be definitely having a certain value. So only this part can be equated equal to 0 to cancel out certain set of harmonics. To cancel the harmonics. So for third harmonic, we can write that 1 minus cos of 3 alpha 1 plus cos of 3 alpha 2, that should be equal to 0, considering n is equal to 3. And now if I want to cancel out the fifth harmonic, I can write 1 minus cos 5 alpha 1 plus cos 5 alpha 2, that should be equal to 0. So we have two equations with two unknowns, alpha 1 and alpha 2. So now if we solve these equations using the iterative technique, so we can find out the value of alpha 1 and alpha 2, which will ensure that the third and fifth harmonic are absent. So alpha 1 comes out to be 17.83 degree and alpha 2 will be equal to 37.97 degree after solving these equations using the iterative technique. So if I go back and look at this waveform, if we select this angle alpha 1 equal to 17.83 and we select this angle alpha 2 such that it is 37.97 degree, then the third and fifth harmonic will be absent from the spectrum of this waveform, right? So if I sketch this spectrum, so spectrum will look like this. Only the fundamental component will exist. Let's suppose it has the magnitude V1. Okay, I am going to sketch Bn over here, and n is equal to 2, no harmonic. Third harmonic is cancelled out because we have calculated these angles alpha 1 and alpha 2 such that there is no third and the fifth harmonic. So I am going to write over here that we have cancelled third and the fifth harmonic. For the cancellation of third and fifth harmonic, we have these angles. So third harmonic will be absent, fourth will be absent, fifth will be absent, sixth will be absent, seventh harmonic is going to exist. So some voltage of that harmonic will be there. Then eighth harmonic will be absent. Ninth, as it is the multiple of third harmonic, will be absent. 10th will be absent. 11th harmonic will exist, right? Then 12th, 13th will be there. 14th will be absent. 15th will be absent because it is the multiple of the third harmonic. 16 and then 17. So you can see from the spectrum, these harmonics, the third harmonic and the fifth harmonic, they are cancelled out and their multiples are also absent. That's why we call it selected harmonic elimination technique. We have adjusted the angles of these edges. I am going to call these one as the edges. This one is an edge, this one is an edge, right? Or you can say the notches. So by introducing the notches or the edges in the quarter cycle, we can cancel out particular set of harmonics. As there are two notches per quarter cycle, so two set of harmonics will be cancelled out. So number of notches define how many set of harmonics we can cancel out from the spectrum of the inverter output voltage. Now if we quickly take the 4 spectrum or the notches per quarter cycle, so how our waveform will look like. So first of all, let's draw the waveform. Let's suppose this is pi and this is 2 pi. This is the center point of this one is the center point of this part, and we are going to construct the waveform in such a way that there are 4 edges per half cycle. So let's start from here. First of all, the center part, okay, this will be at angle alpha 4 because we will be having 4 edges. Then taking the next pulse, let's suppose is over here, its image will also be over here. Okay, so let's mark the angles for these one. This angle will be equal to alpha 3. Similarly, this angle from here will also be equal to alpha 3, and the angle of this notch from this center point will be equal to alpha 4, and the angle of this point will be equal to, let's suppose, alpha 2, and this angle is equal to alpha 2. And now if I draw the last edge, that is, let's suppose this one, so same I will have to draw it over here to keep the symmetry. So let's suppose that this angle is alpha 1 and this angle is alpha 1, right? So we have drawn these pulses in such a way that there exists the quarter wave symmetry because these are centered with respect to this point. So whatever is the angle over here, the same angle is there from this center point. And whatever is the angle of this set of pulse in the first quarter cycle, this is the first quarter, the same set of angles are going to be there in the second quarter, right? Because we know that we are going to construct the waveform which should have the quarter wave symmetry. Now the inverted version of this one, that must be there in the negative part, so I'm going to draw it over here, and I will mark the angle from this point. This is angle alpha 1, right? And then taking the second pulse have this image, right? So the angle of this one is alpha 2, right? And then taking the centered pulse, centered at 3 pi by 2, the angle of this part is alpha 3, and this is at angle alpha 4 from this reference. Okay, so now taking the angles from this side, this angle is alpha 4, and if I draw the pulse over here, this angle will be equal to alpha 3, and this angle will be equal to alpha 2, and finally if I draw that one, please excuse me for the scale, but basically these angles are same. This is alpha 1. So we have the quarter wave symmetry and the half wave symmetry. This is the third quarter, and this one is the fourth quarter. Okay, so now let's consider this part. We have this pulse. I'm going to consider this quarter cycle. So if you look at one quarter cycle, whatever is the area covered, the same area will be covered in the second quarter, the same area will be covered in the third quarter, and the same area will be covered in the fourth quarter. All of these will be same, right? Okay, we will be considering only the first quarter cycle to determine the Fourier series for this one, and then we will see that how we can adjust the angles of alpha 1, alpha 2, alpha 3 and alpha 4 so that we can cancel certain required set of harmonics. Okay, so A naught in this case is equal to 0, AN in this case will be equal to 0, only BN will be evaluated. So let's write down the expression for BN. BN is equal to 4Vs by N pi, 4Vs by pi integration of the first part. First part is from 0 to alpha 1. So our limits will be from 0 to alpha 1 sine of n omega t with respect to d omega t. Then the second part is from alpha 2 to alpha 3, these points. This is alpha 2 point, and this point has the angle alpha 3. So integrating this portion, that is from alpha 2 to alpha 3. So integration of sine of n omega t from alpha 2 to alpha 3 with respect to d omega t. And then taking the last portion of this quarter cycle, that is this one, starting from alpha 4 till pi by 2. So if I write down the integration for this part, so sine of n omega t, integration of this one with respect to d omega t from alpha 4 to pi by 2, right? So as all the quarter cycles are equal, so we have this expression. Now if we simplify this one, so Bn will be equal to 4Vs by n pi minus cos of n alpha 1 plus cos of 0 minus cos of n alpha 3 plus cos of n alpha 2 minus cos of n pi by 2 plus cos of n alpha 4. And it can be further simplified and written as 4Vs by n pi 1 minus cos n alpha 1 plus cos n alpha 2 minus cos n alpha 3 plus cos n alpha 4, right? And I can write it like this: Bn is equal to 4Vs by n pi 1 minus summation of minus 1 power, let's suppose k is varying from 1 to m, where m represents the number of notches or the edges per quarter cycle, minus 1 power k into cos of n alpha k. So when we are considering the first edge, k will be equal to 1, so you will get this term from here, right? When k is equal to 1, when k is equal to 2, you will get the positive cos of n alpha 2. When k is equal to 3, you will get minus cos n alpha 3, and when k is equal to 4, you will get plus cos n alpha 4, and so on for any number of edges per quarter cycle. This equation will be valid, where m is the representation of the number of edges or the notches per quarter cycle, and in this particular example m is an even number, right, if you extend it for large number of pulses or edges. Okay, now from this we can write down the equations by which we can cancel out particular set of harmonics. So if we want to cancel out the third harmonic, then this part should be set equal to 0 for n is equal to 3. So for n is equal to 3, I can write 1 minus cos 3 alpha 1 plus cos 3 alpha 2 minus cos 3 alpha 3 plus cos 3 alpha 4, that will be equal to 0. For fifth harmonic, I can write 1 minus cos 5 alpha 1 plus cos 5 alpha 2 minus cos 5 alpha 3 plus cos 5 alpha 4, that is equal to 0. Then for seventh harmonic, 1 minus cos 7 alpha 1 plus cos 7 alpha 2 minus cos 7 alpha 3 plus cos 7 alpha 4, that will be equal to 0. And for ninth harmonic, but ninth is the multiple of the third harmonic, that will be cancelled out by the cancellation of the third harmonic. So I am going to consider the 11th harmonic, cos 11 alpha 1 plus cos 11 alpha 2 minus cos 11 alpha 3 plus cos 11 alpha 4, that should be equal to 0. So by using the iterative technique, if we solve this one and we calculate the value of alpha 1, alpha 2, alpha 3 and alpha 4, and we generate gate pulses for our inverter in such a way that we get this waveform at the output, because now we have calculated the angle alpha 1, alpha 2, alpha 3, alpha 2, alpha 1, alpha 2, alpha 3 and alpha 4, and for one quarter cycle we have completed the calculations. So we can now set these angles as well. This is the angle alpha 1, this is the angle alpha 2, this one is the angle alpha 3, this one is the angle alpha 4, and similarly this is alpha 1, alpha 2, alpha 3 and alpha 4. So we can calculate all of these points and we can decide about the gate pulses for the full bridge inverter, so that we get this waveform at the output of the inverter. So when we will get this waveform, there will be no third, fifth, seventh and the 11th harmonic in the inverter output voltage waveform. Okay, so we can cancel a certain set of harmonics. That's why we are going to call it selected harmonic elimination technique. So far we have seen the examples in which we have considered even number of edges per quarter cycle. Now let's take an example in which there are odd number of edges or the notches per quarter cycle. So odd number of edges per quarter cycle. So first of all, let's draw the waveform for that one. So let's suppose that this is half cycle point, this is 2 pi, and this one is the center point of this one, and this is the center point of this part. Okay, now let's first of all draw a pulse centered at pi by 2 and centered at 3 pi by 2, and let's draw another set of pulse over here like this. So same pulse will be drawn over here, and same pulse will be drawn over here, and the same over here. And let's suppose that this angle is alpha 1, so this angle will also be alpha 1. This angle is alpha 2, this angle will be alpha 2, and this angle is alpha 3, this angle will be alpha 3. Similarly over here, this angle is alpha 1, this angle will be alpha 1. This angle is alpha 2, this angle is alpha 2, and this angle is alpha 3, this angle is alpha 3. So we have constructed the waveform in such a way that there exists the quarter wave symmetry and the half wave symmetry. So whatever is the width of this pulse, same is the width of this pulse, same is the width of this pulse and this pulse. And whatever is the width of this pulse, same is the width of this pulse. So there exists the quarter wave symmetry and the half wave symmetry. So A naught is equal to 0, An is equal to 0, we need to calculate Bn. So now if I write down the expression for the Bn of this waveform, so I can write it like that Bn will be equal to 4Vs by pi integration from this point alpha 1 to alpha 2. So from alpha 1 to alpha 2 sine of n omega t with respect to d omega t plus integration from this point till this point, and this is the angle, and this has the angle alpha 3, this has the angle pi by 2. So integration from alpha 3 to pi by 2, integration of sine of n omega t with respect to d omega t, and a bracket set over here. Okay, so now if we simplify this one, the Bn will be equal to 4Vs by n pi, and this will be equal to minus cos of n alpha 2 plus cos n alpha 1 minus cos n pi by 2 plus cos n alpha 3. And by further arranging these terms, I can write it 4Vs by n pi cos of n alpha 1 minus cos of n alpha 2 plus cos of n alpha 3. Right, so how many edges we have, edges or notches per quarter cycle? If you look at this waveform, in this part you have one edge, this one, second edge, and the third edge. There are three edges, so you can cancel three set of harmonics. Similarly, three edges over here in the second quarter cycle, in the third quarter cycle, three edges, equal distances. Similarly over here, so you have three edges or notches per quarter cycle, and that's why you can see the three terms over here: cos n1, cos n alpha 2, and cos n alpha 3. And in generic form, I can write down this expression like that Bn is equal to 4Vs by n pi, and if I say that there are m number of notches or edges per quarter cycle, so summation will be there from k is equal to 1 to m. To adjust this sign, I can say minus 1 power k plus 1 into cos of n alpha k. So this expression can be written like that. So this is the main equation that is generic for any number of odd edges, where m is odd in this case, and m represents the number of edges or notches per quarter cycle. Okay, so now from this we can say that we can cancel three harmonics, three set of harmonics. Let's suppose that third harmonic n is equal to 3. So for that I can say that this part should be equal to 0. So now let's write down the equation: cos of 3 alpha 1 minus cos of 3 alpha 2 plus cos of 3 alpha 3, that should be equal to 0. For the fifth harmonic, cos of 5 alpha 1 minus cos of 5 alpha 2 plus cos of 5 alpha 3, that should be equal to 0, and then cos of, let's suppose, 7th harmonic is to be cancelled. 7 alpha 1 minus cos 7 alpha 2 plus cos 7 alpha 3, that will be equal to 0. So by solving these three equations using the iterative technique, alpha 1, alpha 2 and the alpha 3 will be computed, and using these angles, if I come back to this waveform, I generate gate pulses in such a way that the gate that the pulse width are according to these angles. So our spectrum will be consisting of only harmonics above 7. Third and its multiples will be cancelled out. Fifth and its multiples will be cancelled out. Seventh and its multiple will be cancelled out. So we can cancel the selected set of harmonics using this technique. What we will have to do, we will have to develop a quarter wave and the half wave symmetry, and then we will have to calculate the angles, and then we will have to generate pulses from our microcontroller or microprocessor for the switches in the inverter circuit, so that output voltage waveform is what that we have decided over here, right? And if this waveform is appearing at the output, we have the controlled spectrum, we have controlled the harmonics in the output waveform. So far we have seen the unipolar inverter waveform. Now we are going to consider the bipolar inverter waveform and selected harmonic elimination for bipolar inverter. So in the case of bipolar inverter, that you can see over here, we will be switching between plus Vs and minus Vs, right? So the inverter output voltage waveform is shown in front of you, but we decide the pulses in such a way that the angles remain same. This angle is alpha 1 and then this angle is alpha 1, that you can observe. Similarly, the angle of the second notch or the second edge, that is same from the center point as well as from this reference point in the positive half cycle as well as in the negative half cycle. So this is our first pulse, first edge. This is our second edge. There are two edges per half cycle, per quarter cycle in this waveform, and they are at the same angle. This is angle alpha 1 and this is angle, this edge is at angle alpha 2, and same is there for the case of the second half cycle, negative half cycle. Okay, so you have the equal angles. So for this one, if I write down the expression for Bn, so that will be starting from 0 to alpha 1, the first part, that is this portion, then integration of this portion, that is from this part, that is from alpha 1 to alpha 2, but in this our sign will be negative because our output voltage is minus Vs, and then from alpha 2 to pi by 2 our output voltage will be plus Vs, so our sign will be positive for this integration. So if we simplify this one, I can write down the Bn with the help of this expression. And now for the cancellation of the third and fifth harmonic, I can set up two equations looking at this one, that this should be equal to 0. So from here you can see, if we say that n is equal to 3 and that is set to be 0, means you want to cancel out third harmonic, so you have this equation, and for n is equal to 5 you will be having this equation. So solving these two equations, you will get alpha 1 equal to 23.62 and alpha 2 is equal to 33.33. So with these angles, your spectrum will not be having any third harmonic and its multiple or fifth harmonic and its multiple. Okay, now let's discuss the more number of edges or notches per quarter cycle for the bipolar output. In this you can see that you have 4 edges, the first edge, the second edge, the fourth edge, and the first, second, third and fourth edge in the quarter cycle. Right, in the second quarter cycle you have the same angle. This is edge 1 at angle alpha 1, this is at angle alpha 2, this one is at angle alpha 3, and this one is at angle alpha 4. Similarly, in the third quarter cycle, this one is of angle alpha 1, angle alpha 2, alpha 3 and alpha 4, and in the last one, this is alpha 1, this is alpha 2, this one is alpha 3 and this one is alpha 4. So if we write down the expression for Bn, considering the first quarter cycle, that is this one, so this is our first pulse from 0 to alpha 1, and then from alpha 1 to alpha 2 we have the negative part, then alpha 2 to alpha 3 we have the positive part, then from alpha 3 to alpha 4 we have the negative part, and then from alpha 4 to pi by 2 we have the positive output. So if we simplify this one, we will get this expression for the Bn, and in this we have considered even number of pulses. So this expression is valid when m is an even number, where m are the number of edges or the notches per quarter cycle. So from here we can write down for 4 equation, because we have 4 variables, alpha 1, alpha 2, alpha 3 and alpha 4. So we can cancel out 4 set of harmonics. So these are the equations for those ones, and if we simplify these equations, so we will get alpha 1, alpha 2, alpha 3 and alpha 4, these ones. And if we construct these waveforms with these calculated angles, we apply gate pulses to our inverter in such a way that this waveform appear at the output, which has the quarter wave symmetry and the half wave symmetry. So we will get rid of 4 set of harmonics at the output of the inverter. Now let's move to odd number of edges or the notches in the bipolar. So that you can see over here, first edge, second edge and the third edge, and these waveform, these pulses have been arranged in such a way that we have the quarter wave as well as the half wave symmetry. So for the first part we have the angle alpha 1, and if I look at its equivalent, so its equivalent is this one, it is at angle alpha 1, and its image in the third cycle is this one, and in the fourth cycle, quarter cycle, it is this one. And if we look at the second pulse, this will be having the angle alpha 2, the same angle will be there in this second quarter, and in the third quarter it will be having the angle alpha 2, and in the fourth quarter it will be having the angle alpha 2. And then looking at the third part, this is having the angle alpha 3, this has the angle of alpha 3, and similarly this one is of alpha 3 and this one is of alpha 3. And then considering the last part, that is this one, that is from alpha 3 to pi by 2. Similarly this one is from alpha 3 to pi by 2, over here it is from alpha 3 to pi by 2, and this one is also from alpha 3 to pi by 2. So if we write down the expression for Bn for this particular case, so Bn will be given by this one, from 0 to alpha 1 it is minus, and then from alpha 1 to alpha 2 it is positive, and then from alpha 3 from alpha 2 to alpha 3 it is negative, and then from alpha 3 to pi by 2 it is positive. So if we simplify, we are going to get these equations. So Bn will be given in generic with the help of this expression, where m is the number of edges or notches per quarter cycle, and it should be an odd number. So by adjusting the angle alpha 1, alpha 2 and alpha 3, we can cancel out 3 set of harmonics at particular instant of time. Okay, now the last slide is related to 60-degree PWM. In this case, 60-degree PWM means our center pulse will be of width of 60 degree, which is centered at pi by 2. So this angle will be fixed. This is pi by 3 and this will be 2 pi by 3. Similarly, this will be of width 60 degree. So its lower limit and the upper limit will be fixed, and the other notches or the edges will be introduced to control the set of harmonics. What is the advantage of 60-degree PWM? That we will be having the higher voltage as compared to the previous techniques that we have discussed. Okay, so now let's look over here. The first pulse that is introduced, here you can see the angles alpha 1 and alpha 2. Alpha 1 is the starting angle, alpha 2 is the ending angle. Similarly over here the angles are alpha 1 and alpha 2, and the same will be there over here. If I mark the angles for this particular case, this angle will be alpha 1 and this angle will be alpha 2. Similarly this angle will be alpha 1 and this angle will be alpha 2. And then considering the second pulse and or the third edge, so I'm first of all going to highlight all of these, this one and this one. This was the first set. Okay, so now if we look at the angles, so angle for the second pulse, this will be equal to alpha 3 and this will be equal to alpha 4. Similarly from here this will be alpha 3 and this will be alpha 4, right, and same will be there that you can see over here, alpha 3 and alpha 4. Then for the last pulse that is shown over here, we have this one. Let me take a different color for this. This pulse, it's equivalent over here in the second, third and the fourth one, so the angles will be same. So after marking all the angles, now if we calculate Bn from alpha 1 to alpha 2, it is positive. Then from alpha 3 to alpha 4 it is positive. From alpha 5 to alpha 6 it is positive, and from alpha after alpha 6 we have pi by 3 to pi by 2 because center pulse is of width 60 degree, right. So now if we simplify, we are going to get this expression for the Bn, and this is said to be the 60 degree PWM technique because our center pulse is of the fixed width of 60 degree across the pi by 2 or 3 pi by 2. So number of edges or the notches in this are odd because you can see over here first edge, second edge, third, fourth, fifth, sixth and the seventh edges of the center fixed pulse. So 7 edges in the first quarter cycle, 7 edges in the second quarter cycle and so on. So in this one part you can see over here is constant and the other terms are dependent on the number of pulses. So in generic form your Bn will be given by this expression. So m is the number of notches per quarter cycle, and by now calculating the angle alpha 1 and alpha 2, 3, 4, 5, 6, you can cancel out a particular set of harmonics from the spectrum of this voltage waveform. So if I summarize this lecture, in this we have discussed that how we can cancel different set of harmonics from the inverter output voltage by introducing the edges or the notches per quarter cycle. That may be a bipolar inverter, may be a unipolar inverter, there may be even number of edges or there may be odd number of edges. Any combination can be used to control the harmonic or the spectrum in the output voltage waveform. In this way you can improve the quality at the output of your inverter because you are controlling the spectrum, you are controlling the harmonics. So THD, voltage THD can be controlled, current THD can be controlled by controlling the harmonics at the output of your inverter circuit. So this is one of the PWM techniques and it is very efficient when you are using the microcontrollers, simple low computational power microcontrollers, because you can pre-calculate all of these angles and you can program your microcontroller, their timers to generate gate pulses for your switches at the specific time, right. Instead of having the runtime calculation, you will be doing the predefined, you will be using the calculated angles and you will be generating gate pulses for your inverter circuit. So for implementation with the low computational power microcontroller and processor, this is the best PWM technique. Okay, so this has been used in number of applications, in the motor drive applications, in the grid tied inverters, and later on in the upcoming lectures we will discuss those applications in detail. That's all from this lecture. Thank you very much.